Today, we're facing a common array manipulation task, duplicating zeros. The twist? We need to do it in place, modifying the original array without using extra storage. This seemingly simple requirement often hides a subtle trap. Let's see how to navigate it efficiently. The problem asks us to modify a given array of integers. Whenever we encounter a zero, we must duplicate it, shifting all subsequent elements to the right. Elements that fall off the end of the array are simply discarded. The modification must happen directly within the input array, without allocating a new one. Think of it as inserting elements dynamically. A straightforward but inefficient approach involves iterating through the array. When a zero is found, we shift all elements from that point to the right by one position, then insert the duplicate zero. This shifting operation itself takes linear time for each zero. If there are many zeros, or zeros appear early in the array, we're repeatedly shifting large portions. This leads to a quadratic time complexity in the worst case, as each shift could involve iterating through nearly the entire remaining array. Space complexity would be constant if done purely in place, but often this leads to a temporary auxiliary array for easier handling, making it linear. The optimal solution uses a two-pointer approach. First, we determine the final length of the valid portion of the array after duplication, and count how many zeros will be duplicated. We use a fast pointer to traverse the original array, identifying zeros and effectively calculating where the slow pointer should end up in the modified array. The key insight is to work backwards from the end of the array. Once we know the final position of the last element, we iterate from the end of the original array towards the beginning. If an element is a zero, we place two zeros at its corresponding duplicated positions in the modified array. If it's a non-zero, we place it once. By moving backwards, we ensure that we're always writing to positions that haven't been processed yet, preventing overwrites. Let's trace with an example: 1, 0, 2, 3, 0, 4, 5, 0. First, we count zeros that fit. We find 3 zeros. The array length is 8. After duplicating zeros, the last two elements will be pushed out. Our effective last index in the original array that will contribute to the final result is index 5, holding 4. Now, we iterate backwards from that effective last index. At index 5, we have 4. This 4 goes into its final shifted position. Next, at index 4, we have a 0. This 0 needs to be duplicated, so 2 zeros are placed. We continue this process, placing 3, then 2. When we hit the 0 at index 1, it's duplicated. Finally, 1 is placed. This backward pass correctly handles the shifting and duplication. The final array will be 1, 0, 0, 2, 3, 0, 0, 4. This correctly reflects the duplicated zeros and shifted elements, all performed in place. The crucial part is accurately calculating the final positions before the backward pass. You'll spot this two-pointer, in-place pattern when the problem asks you to modify an array directly, especially when elements need to be inserted or deleted, causing subsequent elements to shift. The telltale sign is often a constraint on space complexity, pushing you away from creating new arrays. Time complexity is linear, big O of n, due to 2 passes over the array. Space complexity is constant, big O of 1, constant time, as we modify the array in place. This two-pointer technique for in-place array modification is super common. Try the next problem that involves array shifting or deletion, same pattern applies. Subscribe for more concise DSA explainers.